Hello and welcome. This is going to be the first lecture that we are recording for this course, PHY 422A, and we are on the 20th of January 2021. So this is going to be the part. So as I said, the group is the course is broadly divided into two parts. First part where we do group theory, and in the second part where we do partial differential equations. Now, so we at first would like to focus on group theory. And as I was saying in this session that we had just a few minutes ago, group theory is central to the understanding of symmetry. I mean, group theory is central to the understanding of physics as we know it. So nature around us is actually governed by four fundamental forces. There is electromagnetism, there's a strong nuclear force, there's a weak nuclear force, and there's gravity. So as it happens, so what we do, so again, I'm reiterating what we spoke about just a while back, but we want to understand physics at very small length scales as long as very large length scales. So very large length scales and so on is governed by classical physics. That's fine. We understand it reasonably well. When we go down very small, we have to understand how to how this fits in with, I mean, how our classical theories fit in with, I mean, quantum mechanical effects. And that gives rise to the framework where we understand the physics of the small is quantum field theory, and that is how we actually understand. I mean, how we understand the basic building blocks of nature. So, very interestingly, what happens is, these things, their symmetric considerations are at the heart of all of this. So if we want to understand, the way we do physics is that if you are given a system, the way we want to think about it is you give me an action, and I try to derive everything else from the action. Okay, but how do you fix up an action, if you wish? So for that we have to actually try and understand this as we try and understand what the symmetries are, and we try and write down the actions from there. Now the principles in which you can make symmetries link up with what is, I mean, so how can you get symmetries? What is the language by which we understand symmetries? The language in which we understand symmetries is going to be group theory. And as we will go ahead, we will learn about finite groups. We'll learn about things called Lie groups and Lie algebras. It turns out that are the simplest of examples in the Lie algebras that we're going to do later on in the course are fundamental to the understanding of these four forces that I spoke to you about. Electromagnetism is governed by something you'll know as U1. There is going to be something called SU2, which actually governs what happens for weak interactions. There is going to be SU3 for what actually happens with strong interactions. And we'll also speak about the Lorentz algebra and the Poincare algebra. This is what accounts for gravity in a sense. We will not get to all of that, but I'll try and give you a run through of, when we get to trying to understand this, at least I'll try and give you some ideas of this. So without further ado, let's try. Let me share my screen, and let me try and move on with what I have to say, today. So yes, so what I write here is that symmetries. Symmetry is one of the most fruitful principles in science. So basically, you know, uh, I mean, a large part of theoretical physics today is a sort of pursuit of symmetries, and trying to understand things through symmetries. I go on to write that symmetry is what makes study of science beautiful. And beside this aesthetic appeal, if you wish, symmetries actually help us making precise quantitative predictions about various physical systems, which can then be compared with experiments. So what is a symmetry? So symmetry is can be actually defined as the mappings of physical states of a system, which leaves the dynamics invariant. Okay, these operators that you have must be invertible or infinitesimal analogs of invertible mappings. We will get to why we want infinitesimal analogs of invertible mappings as we go ahead. So some other fundamental observations can be made. So you can so this is I mean you can have the so when you compose two such mappings, this mapping is always going to be associative. So what does the associative mean for those of you who are not very at home with these terms? It just means if you look at three maps, you compose X with Y and then with Z. It doesn't depend on the order in which you do it. So this can be this would be equivalent to X composed with Y, Y composed with Z. You do this operation earlier. So then there is also going to be something which is the identity map that is going to trivially respect. So if you have, that is going to leave the dynamics invariant. And lastly, these mappings are also going to be assumed to be invertible. Okay, so this is the way the mathematical structure of a group is going to arise in symmetry. So this is where the mathematical structure of a group arises in a very natural way. Okay. So now let's just move ahead and say a little bit more. So in a lot of examples, like translations and rotations, for example, the group elements actually describe symmetries of a system that can be labeled by something which is not discrete. It's a, continuous thing like the translation vector or the angle of rotation, right? So, and these group elements depend on this particular parameter that I called alpha here no, this is not an alpha, this is an A, in a sort of differentiable manner. So in this situation, actually, one can speak of infinitesimal symmetries. These infinitesimal symmetries are also called the, generators of the symmetry, as you can recover the entire group all the elements of the group from these infinitesimal symmetries. We will obviously have more to say about it as we go ahead. We will learn this in much more detail. One of the basic ingredients of a group is the operation of multiplication. So what does this do? Given two particular group elements, this sort of associates that with a third one. So there is also an infinitesimal counterpart of this, where two infinitesimal symmetries actually give a third infinitesimal symmetry. But this particular operation of infinitesimal symmetries, as we will see going forward, does not really require all the properties of a group, group multiplication. We will see this as we go ahead. And this is why one needs to introduce this mathematical structure of an algebra. So when we are doing things infinitesimally, we'll not be speaking about groups anymore, we'll be speaking about algebras, okay? So you would be able to expand things, around zero, for example, and that the local symmetries out there would form something which is called the algebra. We will see this, but we will see this more clearly. But let's just try to understand this a little better, okay? Okay, so to characterize an infinitesimal symmetry, as I was saying, it's sufficient to look at so these group elements in some small neighborhood of the identity of the group. So you look at some small neighborhood of the identity of the group, and suppose for example, let's call this so you're given this sort of continuous parametrization of these group elements. So there is this so that's what we're doing here. We have this map. So there is so this group elements gamma are parameterized with this t, with t is a real number, but t equal to 0 gives you this this particular identity element, okay? So what is going to happen is that so this particular parameterization should be such that if you have gamma of t1 and gamma of t2, they should satisfy gamma t1 multiplied by gamma t2 is gamma t1 plus t2. Now, an infinitesimal symmetry will be described by the not the function, but the derivative of the function gamma t at t equal to 0. So what is going to happen is that when you want to know these things that I call these generators, it's not necessary at all to actually know gamma t for all the values of t. It's also not necessary that it be gamma t's would be defined for all values of t. It only it just suffices to have a function that obeys this form, okay? And that's defined in some small neighborhood of t equal to 0. So this particular function is going to be called a local one parameter group, okay? So what does this indicate? This indicates something very, very deep. It indicates that symmetries of a physical system may not be described by groups at all. It may be such that these are defined by only the local properties, which is where the algebras actually are important. So we will do this in great detail as we go forward, and we will see that when we are speaking about these sort of continuous groups that we have in mind, what we will do is we will speak about we will try to we will be speaking in terms we'll make this distinction between Lie groups and Lie algebras, okay? So these are the distinctions that you'll see moving forward. And a lot of the physics, as I said, was that the fundamental forces of nature are dependent not on the Lie group structure but on the Lie algebra structure. So it's more of a local thing. Okay, we will understand this, and we will do this as we go ahead. But let's try and understand something that you guys are more familiar with, if you wish. So one example is let's understand symmetries in classical mechanics. Let's look at the Lagrangian first. So remember what a Lagrangian is, right? So the Lagrangian description, a system is characterized by this Lagrangian L, which is a function of these QIs, which are positions, and by the tangent vectors to this position space, which you know better as velocities, which are the qi dots. Okay, and you have these Euler Lagrange equations that you all are familiar with. And now suppose you have a real number s, okay, and you have it in some neighborhood of zero, such that s belongs to some s is in some epsilon, you know belongs to the range minus epsilon to plus epsilon. And now suppose that for this there is a mapping hs of this position variable. Oops, sorry. And this maps q to hs of q. Okay. So if there is a mapping of this, this is going to induce a linear mapping hs hat of the q dots as well. Okay. So that's straightforward. And what we will say, we'll say that Lagrangian is invariant under this transformation if for any fixed s, you have a function fs, which is dependent on q dot and t, that can also depend on t, okay? Such that the Lagrangian, in terms of this hsq and h hat sq dot, gives you L of q dot plus del t of fs. This extra term, can be allowed because it does not change the equation of motion. The only thing that this can affect is when you integrate over time, the total derivative actually gives rise to a surface term, and this is only something that receives contributions from the boundary of the time interval, right? This is something that you guys know, but I just wanted to reiterate this. Let's take this forward, okay? Now, I mean, linked hand in hand with symmetries are conservation laws. So there is something called, Noitas theorem, which you know, which you have at least heard of. Let's just go through this. So the invariances of this above type gives rise to conservation law. This is known as Noitas theorem. So let's look at this. So we have a mapping phi which of this sort, such that for each q you have a phi of t. So this is a mapping from a time interval to position space, and this is a map, and this is what is called a path. Okay. So this is something that you guys know well, but yeah, this is just written in a little more formal language. So now what we can do is we can use symmetry to map one path phi to a new path phi of s. So what is it going to do? So this is a map, phi of s, which you are going to, so if this is h of s, which is composed with phi. And now what happens is that you have a new path hs of phi of t. Okay, that is what has happened. Okay, so you had a path phi of t, and now you have a new path hs phi of t. Very good. This way, what we can do is we can obtain a family of paths, one for each value of s. And the invariance, what it does, it says that the value of the action for the path phi of s is going to be independent of s. Okay, if this is a symmetry, right? So in particular, If the path is a solution of the equations of motion, then the action is minimal on phi, and it's minimal also on any other path phi of s which is related to phi by this symmetry that we have just said. All right. So what are we doing? We have is particular. Let's just remind ourselves that you have some s which takes values in the small neighborhood around 0, and you have a mapping which maps q to hs of q, and and similarly so that is the symmetry, that's the uh, transformation. So that induces some hs hat which maps q hat, I mean q dot to hs hat of q dot, and a Lagrangian is said to be invariant under this for any fixed s if there exists a function that follows if there exists a function f such that this is true. Okay, this is true because there are, I mean, you could always add this. This is not going to change the equations of motion. All it can affect are things at the boundary. Now what are we doing? We are associating we want to associate a, 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 a path as, so we are associating there's a mapping from a time interval to a position space, and this is a path. And now we are looking at symmetries on this. So a path phi is going to be related to another path hs of phi. So these two paths are now related by symmetry in a very similar way that Q was related to the thing for a specific moment of time. Now we are relating two paths. And this is going to be true for every value of S. Okay. So this means that the value of the action for the path is going to be independent of S. In particular, as I again stress, if phi is a solution to the equation of motion, then the action is minimal for phi. It's also minimal for any path phi of s. Okay. Now to investigate this whole family of paths, it would be useful to actually treat this a variable t, which parameterizes the path, and the variable s that labels different paths on the same footing. So let's introduce a function phi of two variables such that this s is going to be given by this map. Okay. So now let's look at what we have been saying. Suppose so this the value of the action is going to be independent of of s. So del s of this is going to be equal to 0. So now so let's just do the math here. So you just take this through, and what you find is this expression here. Okay. Now let's focus on cues where now let's actually try to use Euler-Lagrange equations. So what you can do is you can replace del L del Q by ddt of del L del Q dot. Okay. So now we have just replaced this with this, and the rest of the thing stays the same. And then it's easy to see that you can actually write down this in the form of ddt of something which is just this. Okay. Now you see that ddt of something is equal to 0 is something that you get. So this particular thing is going to be invariant, is going to be this, we call this Q. So this is going to be independent of time. So Q, which is del L del Q dot, which is del phi del S minus del F S del S. This is a conserved quantity, and it will not depend on time. So this Q is something that is good, that we're going to call the Noether charge. Okay, very good. So what have we got? So we have got that if you're given a symmetry, in that case, what we find is that this symmetry leads you to a conserved quantity. Okay, so it's a bit more formal than you perhaps have seen earlier, but this should be a nice way to. I mean, this should be a straightforward. I mean, enough thing that you guys can follow. Very good. So let's do an example, and then we'll stop for this particular class. Let's suppose you are looking at a motion of a particle in 3 dimensions. Okay, 3 flat dimensions. You are in R3, as you guys all know and love. So the action for this point particle is obviously minus half mx dot squared minus v of x. Okay. Now suppose the potential is actually invariant under a shift of x going to x plus sa. Okay, so that means v of x plus sa is equal to v of x for all s. Okay, so then it's clear that the action, I mean that the Lagrangian L is also invariant under this same symmetry, I mean transformation. So what is happening is that you have hs as x goes to x plus sa, and if you are looking at x dot, this is just clearly equal to 0, and hs hat is just the identity map. If you just substitute this back into the equation, what you will find is fs is also equal to 0. I urge you to try and sit and do this exercise. Now, so what do we have at the end of the day? What we have is that del phi del s, which is going to be just dhs by ds. This is just a. Okay, this is just a. So you just need to look at this particular transformation, and you just have this a vector here. So what are we doing? We're just looking at what are we want to find out, for example, what Q is, and what Q is given by this, and as we have seen, Fs is equal to 0. So this just, so what is going to happen is that so we will find that phi of phi is, del phi del s is dhs by ds. This is just a. So what we have, you plug this back into Q, and you see what you're going to get. This is just mx dot, and here, so this is just mx dot, and this is a. So what you find is that this conserved charge, as you can see from here, is going to be just the momentum, I mean angular momentum in the, I mean a direction, right? So that's this is what you have, what you know that is going to be true. Of course, this is just done in a more fancy way, and I'm sure you, I mean, you can just sit down and figure this out. It's done for you in here, but so let's just say, so Noitas theorem here shows us that if you have any I mean, if you have a differentiable family of symmetry transformations, I mean, any such thing yields, I mean, conservation law, and it yields a corresponding conservation charge. Translational invariance, as we have been seeing, is essentially something that leads to conservation of momentum. And rotational invariance, this is something that you know, of course, again, leads to conservation of angular momentum. Funnily enough, this is something, let me just end with this. Uh, there can be charges, conserved charges that are non-Noetherian. For example, these are sort of like, for example, there's things called topological charges. These appear when you have sort of, configuration spaces which are not connected. Um, so, so what do I mean by this? I have written something down here, and so yeah, so let's not go into this. I mean, I can of course say more about this when you, if you have any things to ask about this. But there can be several sorts of you know I mean, it's not necessary that conserved charges all have to be Noetherian at the end of the day. Okay, so that's what I had in mind for the first bit of the first lecture, and we shall see more of symmetries and their sort of their role in first classical mechanics. We saw the Lagrangian today. We will see a bit more. We will see what happens when you're looking at the Hamiltonian next. And we will also go into quantum mechanics, but let me try and break this up a little bit because this lectures may be a little harder. I mean, at least from what I remember the first time around when I gave this lecture. Um, at one go, it was probably an hour and a half or something like that. These video lectures, I think, pack in a lot more than in a usual class. So let me not go, overboard and give you something very, very long. So remember, so what I want to end with today is, remember the fact that so we are doing group theory because we want to understand symmetries. And the language in which we are going to understand symmetries is the language of group theory. And what we started off by saying we're going to try and do this more is, I mean, I just gave you a little flavor that you might not always need the whole group structure. It may be of importance just to look around some particular neighborhood and understand what's going on out there. And this is where the sort of ideas of algebras also appear. We'll be doing this in a in a lot of detail when we go ahead with the course. But we also saw, for example, how symmetries arise in classical mechanics. This is something that we try to make it a little more formal. And this the idea that this Noether theorem and how symmetries are linked with conservation laws. And as you know, we just did a little example where translational invariance was linked to conservation of momentum. And you guys also know that rotational invariance leads to conservation of angular momentum. So that's it for now. And for the next installment, we shall be looking more at symmetries and group theory before we move on to finite groups after this. Okay, so that's it. That's all we have for now. Thanks, and well, see you guys soon, I guess.